This lesson is on continuity. For a function to be continuous, a function has to have all of its points connected. Every point has to connect with the point next to it, basically. One simple way to think of continuity, or of a continuous function, is if you went down and tried to trace the function with your pen or your pencil, you would be able to trace the function without lifting it up. If you have to lift the pencil up even one time, that function is said to be discontinuous or not continuous. Now there are a couple kinds of continuity, and there are some rules for continuity. And we're going to talk first about the definition of continuity, and then go over some of the graphs, what they look like, and the types of continuity and discontinuities that we have. So again, we're looking to find out when functions are continuous, not only the whole function, but also continuity at a single point. Is function f of x continuous at point C, some given point? A function is continuous if all three of these conditions occur. First, f of c is defined. So a function is continuous at point C, at some point C. First off, the point has to be defined. There has to be a value of the function at that point, at that x value. Second, the limit as x approaches c of the function has to exist. So it has to have a limit. The function has to be getting closer and closer to a certain value, height, at that point c, or at that x value c. And finally, the limit at c has to be the same as the value of the function at c. If these three conditions hold true, then the function is said to be continuous at point C. For a function to be continuous on an open interval, it must be continuous at each point in the interval. So here's how you tell if a function is continuous at a point, and if you have an interval where it's continuous at every point on that interval, then it's continuous on that interval. Here are ways where each of these conditions can be violated, can make a function discontinuous or break continuity. First condition is f of c is defined. Well, you have a function here, you have point c, or the x value of c. If you look up, there's a hole in the graph, and there's nowhere on the curve where the function is defined at c. So, if it's not defined, then there's no way it can be continuous, because there's no value there. Second condition, the limit as x approaches c exists. Well, if you're going to here from the left, to here from the right, if the limit doesn't exist, that means the function is going to different points, or there's an asymptote there. So either way, there's a broken continuity. You're going to have to jump your pencil to get there, or if there was an asymptote, you'd have to jump over it. Either way, the function will be discontinuous because you'd have to lift your pencil at that point. Finally, you have a function that has a limit at c, and that c is defined, where both these are good, but they're not equal to each other, as is the case right here. The limit as x approaches c exists, wants to be up here. The function is defined at c, but when they don't equal each other, you have a hole in the graph. So to trace this function, you have to trace, lift, lift again, continue tracing. So therefore, this function is discontinuous. There are two types of discontinuities. Two ways a function can be discontinuous or not continuous. The first type is a removable discontinuity. The second type is a non-removable discontinuity. A removable discontinuity happens when you can either redefine or define for the first time f of c so that the function becomes continuous. Simply by either defining a point or redefining where that point is at, the function becomes continuous. So here we have two removable discontinuities. Right here. If you define f of c to equal this value, you fill in the hole, and then the function will become continuous. Down here is where we have to redefine f of c. Instead of f of c being here, I want to redefine f of c to be down here. I fill in that hole, f of c was redefined, and your function would then be continuous. That break when it happened. One way to think of this graphically is if you have a hole in the graph, that's approached from both sides, that's going to be a removable discontinuity. You can simply redefine C at that hole. A non-removable discontinuity happens where it doesn't matter if you define a function at a different point. There's no way to do that where you'd be able to have a continuous graph, where you wouldn't have to lift your pencil. So this example here, if I define C down here, it doesn't matter, I'd still have to jump to get to it. If I define C up here, I'd still have to jump to get back down there. It's where you have a hole or a closed circle, but they're attacking different points, so you have to jump. Another non-removable discontinuity would be a vertical asymptote, where you have to jump over that asymptote. One point won't help redefine that, making the function continuous. So, removable discontinuity, you have a hole in the graph that's approached from both sides. Non-removable discontinuity, it doesn't approach the same thing at both sides, or it both approaches infinity, negative infinity, or the opposite, and you have an asymptote. When you talk about continuity, you talk about something called one-sided limits. Although a limit may not exist at a point, one-sided limits can exist. The limit as x approaches c from the left side is written as limit as x approaches c with a little negative sign above. That means from the left side, from the negatives, as you approach from this side. The limit as x approaches c from the right side is written with a little plus sign there, meaning coming from this way, coming from the positive. You have a right-sided limit or a left-sided limit. So right here we have a function where the limit as x approaches 2 does not exist. But one-sided limits do exist. The limit as x approaches 2 from the left side, I trace this function from the left, coming from the negative. I want to get here. So the limit as x approaches 2 from the left is 3. The limit as x approaches 2 from the right, coming from the positive direction, you want to get here. So that limit is going to be 1. Even though the overall limit does not exist, the left-sided limit and the right-sided limit do exist. In order for a function to have a limit, the left-sided limit has to equal the right-sided limit. Both limits have to be the same for the function to have an overall limit at that point. To state here, for a limit to exist, limit from the left of the function as x approaches c has to equal the limit from the right of the function as x approaches c. Finally, the intermediate value theorem. This is an existence theorem. You'll see a couple more of these throughout the course. The intermediate value theorem, I'm going to walk you through this and then give you a conceptual understanding. First off, these three conditions have to happen. F is continuous on a closed interval. So whatever function you're talking about must be continuous between two values, between a and b, these two endpoints of some interval. F of a does not equal f of b, meaning the value of the function at the left endpoint does not equal the value of the function at the right endpoint. Either we're higher over here or you're higher over here, but they can't be the same height. The y values have to be different. And k is just going to be some number between f of a and f of b, meaning k is just some height between these two heights. The intermediate value theorem says that there exists at least one number c on that interval such that f of c equals k. What that means is, if you start here and you end up here, and k is some number between these two, if this function is continuous, somewhere along the path getting from here to here, you have to go through k. There has to be somewhere on here where the height of the function is exactly k. That's all I'd say. You can't get from here to here without going through every point between them. Or you can't go from here to here going down without getting through every y value between those two. So somewhere between these 2 points, there's going to be the function will be every value between these two. So you pick any value in here, the function has to equal it somewhere. It could go down and come back up and hit it. It could go up and come back down. It actually could be a function that curves a couple times. It could do it a couple times in between. But the intermediate value theorem states that this must happen at least once if the function is continuous and the value of the endpoints are different.